and it's in full time. It's a sustainable Arctic marine and coastal technology. And the topic of today that I'm going to present is pretty long, but there are actually only 3 keywords. The first keyword is ice load measurement. The second keyword is tactile sensor. The third keyword, RITAS. I'll come consecutively with what they are. First, ice load measurement. As we know that ice engineering is relatively a young science. And lots of our theoretical studies, we have to say that it's rather an explanatory tool instead of a predictive tool. So, in this context, ice load measurement, either it's going to be measurement in the field or measurement in the ice tank, is of high value. And it's quite important to have all these measurement because it can tell us whether our theoretical model is too conservative or too risky. Therefore, we can build our offshore structures more economical and more safer. And also, ice load measurement is very difficult. And because you need a lot of logistics, it's in a remote area. You need to transport a lot of things to such tests, so it's very difficult. And that's the importance and the difficulty of ice load measurement in ice engineering. And you have you have seen that Murray, he presented a lot of measurement in his presentation, and that's extremely valuable. Okay, then talk about ice load measurement. How can we classify them? There are different point of views. One view is that you can classify them as a full-scale measurement or model-scale measurement. Regarding full-scale measurement, Murray also presented this lighthouse, the measurement, and this has been used to measure the ice-induced vibration or the level ice load on a lighthouse. And they have installed several panels to measure the load distribution around this structure. And you can see this is a human being's leg. You can see the scale comparison here. And in terms of model scale measurement, we have done this in just VA, and this is another group of human beings' legs. So you can see the scale comparison here. So this is model scale. And another perspective that you can consider about ice load measurement is either you are measuring the global ice load, or like this in this case. This is founded by Hydrolab 3 in 2010 and done by Tomokona. And you have one hinge here, this carriage here to measure the global ice load. Or you can do it to measure the local ice load, to see the distribution of ice load around the structure. So this is a simplified icebreaker. It has been told through the level ice. And in the icebreaker, in the model icebreaker, we have several panels, and you can measure the local ice load like this. But you can see this spatial variation, the spatial measurement, actually they are not of high resolution. They are very large panels. And this is again founded by Hydrolab 3 in 2011. And some improvement has to be made. Now we have Hydrolab 4. And that's our focus. We focus on model scale measurement and also the spatial ice load measurement. And in this case, we measure the spatial ice load with the second keyword, tactile sensor. So what is a tactile sensor? It's essentially a thin foil like this here, and you can put some load like a human being on top of it. And there is some device to transport what it can measure to display on a computer. And then we are going to use this thin foil to measure the local ice load okay, let's talk about the history. We are not the first one to use this kind of thin foil to measure the ice load on a structure. Actually, this has been extensively used in Japan in the 1990s to measure the local ice load in such tests like indentation test to measure the ice load distribution on a vertical structure, or they measured how the ice load would distribute on the icebreaker, like here along the icebreaker hull. And we are using, and they have been made some conclusions. A lot of experience has been made on this tactile sensor, like its durability. It can be used in rather harsh environment, like this cold environment, and also with water and all these things. And also it can handle pretty well with a dynamic load, like in this range. And also they have very good spatial resolution. So if you can remember that if you measure a local ice load with different panels, the resolution is not as good as the tactile sensor. Tactile sensor can even tell you what's the shape of your footprints. And also the spatial measurement is very consistent. Whether you're measuring here or there, there's some consistency in the spatial measurement. But there are also disadvantages. First, the accuracy is questionable because there is some nonlinearities in the scale, in the calibration. And also the contact area is also influenced, whether you have a large contact area or small contact area. There are some inaccuracies there. But we would like to take advantage of these advantages and try to avoid these disadvantages. And we use the tactile sensor in the RITAS project. Then the third keyword, RITAS. What is RITAS? RITAS is Rubble Ice Transport around Arctic offshore structures, and the detail of which has been presented in Nicolas Serra's presentation. Now we just focus on the application of tactile sensor with the buoyancy box. Okay. The question that we want to answer is that how much rubble accumulation load is on a sloping structure. Murray, in his publication in 1990s, he used the finite element method, and he stated that the rubble accumulation part, this is the accumulation on top of the structure, and it can be decisive than the breaking part, which means that the ice is coming, your structure is breaking the ice. It sounds very terrible. The sound is really scary. Lot of noise, but actually that's not scary. The most scary part is that all these rubble, they just accumulate in front of the structure. It can easily push your structure away and destroy your structure. So this is the question that we want to quantify. How much rubble accumulation load in comparison to the ice breaking part? And we use the tactile sensor. And this is the buoyancy box Nicolas Serra has been presented. We simulate an extremely long and infinitely long, very large, wide structure that there's no rubble clearing here. And we install this tactile sensor on this sloping plate. And you can see we have a very high resolution. And each single sense cell, it's only about 7 millimeter by 3 millimeters. So we have really high resolution in our measurement. And we have, these are details. And a 3D test has been done in a different structure by Nicolas Serra. He has presented in the previous presentation. And then we pushed this structure in level ice. You can see this is a sequence how the ice is filled. So in the beginning, it breaks as expected, and it looks very calm on top of it. But what's beneath these rubbles, they are really accumulating. And then we are able to use this tactile sensor, which cannot be shown here, it's somewhere here, to shed light on how much load is needed to break the ice and how much load is increasing with the accumulation of rubbles. Just a snapshot to show how the ice load is look like. First, this is the tactile sensor, the signal is displayed, and these peaks tells us in locally how large the ice load. So you can see initially there is some contact, maybe partial contact at the water line area. There is some large load, and then the load has a full contact. Gradually the load travels down, and this place is somewhere where the water line is. So the load is traveling downwards a bit long after the water line. And then we took out this is the sloping structure. This is our sloping structure, and this red color is where the tactile sensor is mounted, and this is the water line. And this shaded area is where the ice thickness is. So the ice is this thick. It comes and heat on this structure. And then we were able to measure the load locally in every point around this red line. And then we made some statistics. First, on the left graph, we average every point in time history. We make an average to see how much load is here. So this is the water line. You can see there the biggest load is not happening at the water line. Instead, the load is somewhere beneath the water line, and it's keep fluctuating and keep a same magnitude even below the ice thickness. Okay, and this is this we are not using average. We are not doing any averaging. Instead, we'll pick out each point, the maximum load at each point. So in the whole test run, we take out the maximum load and plot it here. So you can see the maximum load, it occurs within the ice thickness region. So the question is, why the mean ice load it keeps very large even below the ice thickness, but the maximum ice load it happens within the ice thickness. And based on this measurement, we come up with a hypothesis. This is the interaction mechanism. So first we have a level ice come in contact with the sloping structure. It breaks here and it introduces a very huge ice breaking load. This might be the load that we see, the peak load that we see here. But that's not the end of the story, as we have a lot of rubbles accumulating here. So there's just a rubble accumulation pressure here. Besides, this ice piece has been rotated downwards, so it goes down following this plate and goes down. So there's a load peak. You can see that the traveling downwards. This is what we see here. So there is a load peak. It keeps traveling downwards, even beneath the water line. So this is the hypothesis that we got from our measurement. And we made some mathematical study to confirm our hypothesis. That has been published in a different paper. And since we have limited time, so I just condensed everything here and go directly to our conclusion. It's a short presentation, only 15 minutes. But if there's anything that you can take away from this presentation is that, first, rubble accumulation load, it contributes a large portion of the total ice load. That's the first part, which is commonly accepted. But how much it attributes to the total ice load, it can be measured as here. And another thing important to see that how this load is traveling downwards, how it's transferred downwards is because of this ice rotating process. And that's the 3 points that I want to convey out. Thank you.
Impressive presentation. We still have time for questions. No questions? Please say your name and affiliate.
Thank you. Sagonas, UCL. Just a quick question. How did you calibrate the tactile pressure sensor for this kind of application? I'll bring the microphone over to you.
Actually, calibrating the tactile sensor is quite challenging work for us. It's something totally new, and we have to read the manual to see how it can be calibrated. Actually, there are several ways of calibrating the tactile sensor. And you can calibrate it with a dynamic method, or you can calibrate in a static load. And we choose the simplest method, which is by static load. But even by static load calibration, you have two approaches. First, you can calibrate with one single point. Another is that you can calibrate the whole non-linear trend. But in the very beginning, we don't really know how much ice load that we're going to encounter. So we made several calibrations, and during the test, we update the calibration to see which calibration gives us the most sensitive measurement. By sensitive, we mean that the output of the ice pressure is most colorful. By colorful, we mean that it can cover a lot of ice pressures. But let's come back to the ice problem. As you can see that we have different failure mechanism here, ice breaking and ice accumulation. This ice breaking is quite dynamic and it has a huge ice load in comparison to the rubble accumulation load. So as I have mentioned in my presentation, there is a non-linearities in the calibration, which means that you cannot make sure that all the measurement range has the same accuracy. So we have been facing such problems that which range that we should choose. And since we are interested in the rubble accumulation load, so we have been trying to calibrate our tactile sensor to best capture this part of the load possible. But the other range is not so good. Yes.
And now down to the question. If I'm not mistaken, the manual suggests using homogeneous pressure applied over the whole sensor. And you're using that with 2 points, and then you plot the curve over the points, and then you calibrate it. Did you use such a way to apply the pressure or the force, if you like, on the sensor, or you use something else?
I use this, as you mentioned.
Okay. That's all. Thank you.
If you wait there, you will get it back. This measuring equipment I guess that's not only restricted to measure ice load. You can use it for wave load. You can use it for impact load as well. Is that true?
That's what I had as well. That's true, but I have never extended its use beyond ice load. Some people, they were using it to measure the slamming load from wave. Okay. Okay.
Okay, we have time for one final or last question, and then another announcement. So if there are no question, I would like to announce that the bus for the dinner leaves tonight or today at the neck here at 7:15, and from the Hotel Villa Rica at 8 p.m. and from Hotel Lutetia 8:15 p.m. That's the information to you who want to join the dinner tonight. Yeah, I think we had a successful session this afternoon, and I would like to thank all the presenters and the audience for being here. And as we could see, there is a lot to do for the future, and I hope that the work on the analysis of these projects is going on and will be finalized. And then I would like to invite you to think about new projects because we are strongly working on continuation of HydroLab 4, and so then if we are successful with that, then there will be a call for further transnational access proposals. Thank you very much.